Hello, welcome to the IB2d video tutorials. This is tutorial 4, which will cover the basics of data visualization using VisIt, an open source piece of software created by Lawrence Livermore National Labs. As with any open source software, it is freely available. Simply go to the link listed here or simply search for VisIt software download into your favorite search engine. In this tutorial in particular, we will focus on visualizing the Lagrangian structure or Lagrangian points as well as the Eulerian data. Remember, all this data is being saved when we run an IB2d simulation and we get the choice of what type of data we wish to save, which is found in the input2d file. To make this tutorial very useful, I would suggest that you download VisIt and follow along. I'll wait while you download it. Just kidding, please download it, then resume with the video. Next, the example we'll use is in the example skeleton, which remember is that of the oscillating rubber band if you've been following the previous tutorials. If you haven't, just go to that directory and type main2d into MATLAB's command window to run the simulation. It should only take a couple seconds, or about 30. Remember, after running the simulation, this is what we should see inside of the directory. The higher IB2d data gives us the force data onto the Lagrangian structure, whereas the Vis IB2d data gives us more or less the Eulerian data as well as the Lagrangian position data. Now, the other thing I want to draw our attention to was inside the input2d file is where we declare what type of data we want to actually save during the course of the simulation. So if we scroll down to the printing information section, this is where we get to choose what type of data gets stored as well as how often we print the data. So if something is flagged here as a 0, that means we aren't going to store it. However, it looks like in this simulation we're saving everything: vorticity, pressure, the vector field of velocity, the magnitude of velocity, and etc., etc. Just remember, if a quantity is not flagged, the corresponding data will not be saved. The last thing I want to say is that the data produced in an IB2d simulation is in the VTK format, which can be visualized using VisIt, ParaView, or other open source software. So VisIt is not your only option. Now let's go ahead and open up VisIt. So upon opening VisIt, this is what you should see. On the left-hand side will be essentially where we open up each file or the data that we want to visualize. On the right-hand side, I'm sure you could guess it, is where we actually see the visualization. So without further ado, let's jump in and try to visualize some of that data. So if you remember, we're going to be opening an example that corresponds to a skeleton example or the oscillating rubber band. So you can just search through all your files until you come across that particular directory. Once you're in that directory, we basically can visualize either the Vis IB2d data, remember, which is the Eulerian data corresponding to the fluid, things like the magnitude of velocity or the velocity vector field, or even the Lagrangian positions themselves, whereas the higher IB2d data corresponds to the forces on the Lagrangian structure. So first, let's jump right into the Vis IB2d data. Now on the right-hand side here, you'll see all the data written in VTK format, and it's ordered by groups. So first we see omega, which it corresponds to vorticity of the fluid. Next, we have pressure that corresponds to the background pressure field in the fluid. And you can do this for a lot of different quantities, but let's keep scrolling down until we get to lag points and lag connects. The difference between lag points and lag connects is lag points are the individual Lagrangian points, whereas the lag connects, or the lag point connects, are the spring connections between successive Lagrangian points. Let's actually go ahead and open up the Lagrangian points themselves. So just click OK. Now, I'm sure you noticed nothing actually happened. That's because we actually have to add something to our screen. So if we go over to Add, we can click Add, and since we're dealing with Lagrangian data, we can go over to Mesh and just click on Mesh. Still nothing happened. We have to click Draw. And lo and behold, those are our beginning Lagrangian points in the initial configuration. Now we can do a couple things to these points to make them better. If we double click on the mesh, we can change their plot attributes. So for example, if we click this first custom next to mesh color, we could change their colors. Let's make them, I guess, how about green for right now? You can't really see that too well, but if we scroll or if we look down at point type, point size pixels, we can increase the pixels as large as we want. Let's just go to 10. And you can see that we see individual squares. Now we could also change the point type. There's lots of different options. We could click sphere, sphere geometry, tetrahedrons, etc. If you just click sphere, you can see they're now individual rounded off points. Let's make this a little larger, say go to 14 or so. And then we can close this dialog box. Now why don't we go back to Open, and instead this time open up the Lagrangian point connections. If we open up the lag points connect, remember this will illustrate the connections of any springs between Lagrangian points. We again don't see anything immediately happen to our screen, so we can click on Add, and then if we go to Mesh again, we are now on Lagrangian points connect, and we'll be able to add a mesh for the spring connections. Now another dialog box comes up that asks us if we'd like to create an index database correlation. What this means is if we watch a movie of our simulations or frame to frame, that we would want that the lag points connect correspond to the same frames as the lag points themselves. So let's just click yes. Now nothing still happened. Let's click draw. And we can see that kind of a line has come between successive Lagrangian points, just like we set it up in our spring connections or .spring file. And again, we can change these attributes on this mesh. If we double click, we can make this a different color, say make this one pink. And we can change not the point size, but the line style now, because these are straight lines between successive points. So if we go to line width, say 8, we can make that a lot thicker. Now you can surely see that the spring connections are basically covering up our previous individual Lagrangian points. Now we can stack the order or just change the display order. If we right click on lag points connect, we can say make first or make towards first. Now it doesn't matter one of these two options because it'll just put it in front. And you can definitely see now that the lag points individually are the ones on top. Now the moment you've been waiting for. Let's try and play a movie. If we just click over this play arrow, or we can individually try to click through. Let's see what happens if we just click play. Well, we see that we do oscillate towards a circle. However, a lot of Lagrangian points are no longer actually on the screen. We can change this if we go up to View, which is under the Controls panel at the top. If we click Controls, we can go to View, and inside this dialog box, we can change what we see along the axes. Now it's a little hard to see, but basically it goes X minimum, X maximum, Y minimum, Y maximum. So let's just change this all to 0, 1, 0, 1. And then click Apply. And now you can see our full computational grid. And if we play the movie, you can see this oscillate in full frame. Now, beyond just visualizing Lagrangian points or those Lagrangian point connections with springs, let's actually see what the background fluid is doing. So we can go back to Open and basically choose something else to visualize. Let's actually first visualize UMag, which stands for the magnitude of velocity, whereas UX and UY stand for the magnitude of velocity in either the X or the Y directions respectively. So let's go to UMag and then Open. Now nothing happened. We have to go back to Add to actually add that geometry, or sorry, the background color map. On that note, we won't be going up to Mesh anymore. We'll be going over to Pseudocolor and then clicking on UMag. And again, we want to create a database correlation, so click Yes. And draw. What you see here is a color map of the magnitude of the background fluid velocity. We can again play this movie and see what happens. It's making a pretty groovy artistic decoration. Remember, this is a very coarse simulation that we ran, but we can do a lot of things to try and make this a little more visually appeasing. So if we click Stop, we can double click on UMag to see what type of options this can bring up for us. Now the first thing to note was every single frame, the minimum and the maximum values changed. Well, we know that the minimum here is always going to be 0, so we can set that at 0. The maximum though, it looks like in this particular frame, if we look over what the max is, it looks like it's about 1.8. So we could set the maximum, say, at 1.5 and see what happens. Now, for simulations on your own, these will be numbers that you can play with yourself. The other thing we can do is go down to color table, and if we don't like this rainbow color table, because remember people with certain degrees of color blindness have trouble seeing distinctions between, say, reds and greens, we can choose different color maps. And there's a lot that VisIt has to offer. So let's just click on one, say, I don't know, purple and orange, and click Apply. We can also invert the colors. So rather than orange being 0, orange can correspond to the fastest flow, and purple will correspond to slowest. So just click Invert, and you can see what happens. Now if we just click off this, we can again play the movie and basically see what's happening. In this particular simulation, it looks like the fluid that's moving the fastest are where the largest deformations of the Lagrangian structure occur. That makes physical sense. Let's just stop this here. Now, beyond just looking at the magnitude of velocity, there's a lot of other quantities we could look at with color maps. Things like the pressure, the vorticity, or the X or Y magnitude of velocity, even the force data. Let's instead take a look at what's going on with the background velocity field itself. We can do this by opening up the velocity field down in the list that's just called U. So click OK. Again, nothing happens because we need to add it. If you go over to Add, you can click the plus, and instead of opening up Pseudocolor, here we want Vector and U. And we can click Yes, we would like a database correlation, and we can click on Draw. As you can see, we now have a vector field illustrating what the velocity is actually doing of the background fluid. And we can clean this up or make this as artistic as we would like, or visually appeasing. Double click on U. One thing we can do is change uniformly located throughout mesh. And we can change the number of vectors there actually are. Say instead of 400, let's have 4,000. And you can now get a very clear depiction of what the fluid is doing at this particular time step. But there's other stuff we could do. We could change, again, the color map corresponding to where the fastest or slowest velocities are, or we could just make the velocity field constant. Say, let's see what happens if the velocity field looks black. Or we could change this to another color that may be a little more advantageous. Try dark red, maybe even white. But again, these are quantities that you can try and play with yourself. The last thing we can do with the vector field is go to glyphs, and we can change the scale. Of course, increasing the scale makes the vectors larger. Decreasing the scale makes them smaller. The other interesting features about VisIt is that we can scale by magnitude. So if we unclick this, basically what they'll say is every vector will now be the same length and same size. And if we decrease this, say to 0.1, we get still a similar depiction of what the fluid's doing. However, this time we have no idea where the fastest flows are occurring because every vector is the same length. So if we go back to scale by magnitude, we can change the size to get a better idea. So these two quantities, using color maps for things like vorticity, magnitude of velocity, pressure or force data on the fluid grid, or using a vector field to illustrate the actual fluid velocity, are very informative. However, we can clean this picture up even further. So let's do that now. To make this a little more visually appeasing, what we can do is get rid of all this text and these color bars on the left-hand side, and even get rid of the axes information and user information. To do that, we can go up to Controls again at the top of the and click on Annotation. Inside this annotation window, we have a couple options. We can turn off legend, database, and user information, and when we do that, we get rid of all that erroneous text and those color bars. If we click on 2D, we can get rid of those axes altogether. So now we're just left with the image from our simulation. Now it's going to be very weird if you try to resize your screen or save this as a movie. You're going to have a lot of extra white space. So one thing you can do is go back to Controls and click on View. And inside View, go to Viewport and just change these proportions. Instead of 0.2 to 0.95, do 0.001, 0.999, 0.01, and 0.999. And click Apply. You can click out of this viewport dialog. Now basically, if there's any white space surrounding our image, when we save this to be a movie, that white space will also be saved. Whoa. Well, some funky stuff is happening. If we just go click up here to reset view, it'll bring us to a full screen. And we can click on the edge of this to kind of readjust this, and as you can see, just by readjusting this box, it minimizes the white space surrounding it. So now we can go ahead and try to save a movie. Now before we jump right into making a movie, I want to point out one small thing. If we take our active time slider and slide it all the way back to time step 0, a warning box pops up saying the vector plot of variable u yielded no data. What this means is that, well, at time step 0, the fluid is not moving anywhere, so there's 0 background velocity. And essentially, for this vector field, it just doesn't know how to plot that. So we can click Dismiss. To turn that warning off, we can go up to the VisIt selection, click Preferences, and in Preferences, just disable warning message pop-ups. This will come in handy when we're trying to save the movie because otherwise as I'll point out in a few minutes, that dialog box will keep popping up almost repeatedly and we'll be unable to use our computer otherwise while the movie's being created. So now let's go ahead and go up to File and Save Movie. Inside of this dialog box, the first thing we want to do is say, yes, we want to create a new simple movie. Go to Continue. And we can choose the movie format. Here, let's just go with the standard MPEG. And we can click this right arrow to bring it up into our output box. Click Continue. At this stage, we can choose a lot of the movie preferences, such as the frame rate, the first and the last frame, as well as the frame stride if we only want to include every other frame or every 3, every 10 frames in our movie. In this case, let's keep the frame rate at 5, the first frame at 0, the last frame at 75 with the frame stride of 1. That sounds good to me. And click Continue. Next, we can choose the output directory as well as base file name. Rubber band. And we can click Continue. Do we want to be notified by email when this movie completes? We could do this yes or no. The motivation for saying yes is sometimes these movies could take upwards of 15-20 minutes for a single simulation, depending on how highly resolved the fluid grid is, if we're including the vector velocity field, or just color maps, or how complicated the simulation is. In this case, let's just click No and Continue. And if we'd like to continue using VisIt for other things while the simulation's being created, or the movie's being created, we can click this middle option, Now, and use a new instance of VisIt. What this would mean is a new VisIt window will pop up so we can continue using the software, even though our movie will be being created in the background. However, now let's just use the currently allocated processors or the VisIt window we have opened up now and click Done. What you'll notice is this dialog pops up saying the process is being created and we're generating frame by frame in the movie. If we didn't disable that warning pop-up, each of these frames that's being created would pop up another warning, not allowing us to do anything else on our computer at this time. Now this movie will take approximately 2 minutes to be created, and remember, this is a relatively simple example. We're running this on a very, very low resolution grid, so we wouldn't expect it to take too long, but it still takes a little bit of time. I'll check back in once the movie's done being created. Okay, VisIt has completed our movie and it's located on our desktop. Let's go ahead and open that now. Okay, and we can click off this terminal window and terminate it. In opening our simulation, we can just go ahead and play this. And there is a simulation that we created in all of its glory, with a vector velocity field, as well as color map illustrating the magnitude of velocity. I hope this was a helpful video on teaching you the basics of data visualization using the VisIt software. Don't be fooled though, there's a lot more that you can do within this software framework. The next IB2d tutorial will cover the basics of data analysis using the IB2d data analysis toolbox. This will be useful for quantitatively analyzing the data to things like velocity cross-sections, quantifying fluid mixing, or even lift and drag forces. This toolbox essentially helps produce the meat of your desired research study, while those data visualizations that you've just created make wonderful complements to that analysis. As usual, thank you for checking out this tutorial video, and happy computing.